Introduction. So it's my pleasure to introduce Professor Annie Liu. Annie is a professor of computer science at Stony Brook University. Her research is in languages and algorithms and is particularly interested in incrementalization for design and optimization. Annie's lab has many projects for optimizing compilers, interactive environments, real-time and embedded systems, databases, semantic web, distributed systems. And in today's talk, Annie will give us an overview of partial evaluation and incremental computation as meta frameworks and the power of this for systematic specialization and incrementalization of transformation. So take it away, Annie.
Thank you for the introduction. So thank you. I want to thank the organizers for inviting me. I want to first thank the organization so far. Actually, I was very surprised for Fritz's talk this morning saying the preparation for celebrating 30 years of PEPM'. I did receive an email, but I didn't expect that surprise talk. So congratulations to PEPM' for turning 30. So this talk will be quite a span, and most of the work will be about work we've done. I've actually started with even PhD thesis studying partial evaluation until even now, but most of the work are done in the last 20 years at the Stony Brook University. Okay, so first, brief FAQ. Where's Stony Brook? It's about 55 miles east of Manhattan here on Long Island. Okay, so the meta frameworks I'm going to talk about are partial evaluation and incremental computation, particularly the power of the transformations, which I call specialization and incrementalization. Okay, many people to thanks to for people who did fabulous pioneering work, and many people, especially my fabulous PhD students who contributed and helped in our new explorations. Okay, and as I was writing, I was missing some people, so I just put that out there. And of course, for the grant support. Okay, start simple. A computer program is a program. I don't know if you can see my little arrow here, but anyway, it's a program that takes some data and produce some result. You can view it as a mathematical function, like f takes an x and produce a result r. Okay, so that's maybe too simple. So in general, these data can be arbitrarily complex structure. A simple case will be just x1 to xk, like a vector. And the program can continuously take data and produce result. Okay, so partial evaluation. It's this meta framework. That's this function can take all complex data, but it can be separated into two parts or think as two parts, and has computations, of course, on both parts and together. I write in this simple way, but this k and g and h can be very mixed in terms of what they do on x1 and x2. Okay, so you're given such a program. The point was there are two parts, and there will be a particular value v1 for one part of the data x1, expecting many different values for x2. So partial evaluation can think about partially evaluating the input on x1 being v1 and produce some results, say w1. And you plug this in, so the resulting program look like the simple one, right? Specialized program or residue program. So what I'm going to emphasize is the transformation aspect. I use PE specialization, but mainly as transformations. Okay, so partial evaluator or specialization takes f and takes particular value for part of input and produce a new function specialized to that value. Okay, there are a lot of related work that I got carried away actually preparing for this talk, but I saw the talk this morning. Some of them were dated earlier, but these are the earliest one I could find. Okay. So I have to, I have to talk about the slides. I was thinking everybody knows this, and especially all the talks in this morning, but I don't see it. Okay, so the core of compilation, which I consider is the central, very central topics of computer science, is this partial evaluation, which I didn't know until I saw this. So you think about it, if you have a program that the straightforward to think about, there's an interpreter that understand the meaning of this language you're writing the program in, takes the data and produces a result. That's called interpreter. Okay, that takes two parts, a program and data. And then if you apply partial evaluation to this function of first argument, okay, you get interpreter specialized to this particular program. And then this program will take the remaining data and produce the result. Okay, so this thing, whatever you produce, take data, produce result. Wow, that's like no more compiler anymore. So that's a compiled program. Okay, so then you can continue this, right? Partial evaluation first specialized to interpreter and then take the program. So you get this partial evaluation applied to interpret, specialized interpreter and take the program and produce the compiled program. So something takes your program, produce the compiled program, that's a compiler. And finally, you can do this one more time, PE applied to PE, and you get something general, and that thing takes interpreter, produce this thing, which is the compiler. So that's the compiler generated. Okay, I can't help spend this minute on this just because every time I see this, even now, it's just so magic. If you have any questions, you can, of course, ask. I might not see all of them, but I will try to answer at the end. Okay. I seem like I always have to click this tiny little arrow to move forward, and it has a delay in there. Okay, so I'm going to talk about a little bigger. In fact, this is a topic, this is the problem I was given when I started my PhD. Okay, so on programs, you do a lot of things. You start with editing it. Of course, you do syntax analysis, semantic analysis, compilation, do transformation, and finally you execute it. Okay, not just compilation. And if you do interesting analysis, right, trivial ones are not interesting. These analyses are expensive. And as you edit the programs, these analysis needs to be done repeatedly as the program is changed. So you must do this analysis incrementally. Okay. In fact, my thesis advisor, Tim Teitelbaum, he started this work, probably, all this related work and for his thesis, but at Cornell has this Cornell synthesizer generator. So you want to do something general. Indeed, this is a list of his students, all the papers I studied. Okay, ComReps study attribute grammar and incremental attribute evaluation, because attribute grammar can write all kinds of semantic analysis. Okay, and then more general, you think about program as a database. You do incremental view maintenance. That's Susan Howard's thesis. And going even more, think about it just program as graphs. Everything is graph, right? Objects and relationships. So incremental graph evaluation, Roger Hoover thesis. And Bill Pill continued, just as program or functional programs to function caching, which led to his invention of skip lists. And even more fundamental lambda calculus, incremental lambda evaluation, like John Field did for his thesis. Okay, so indeed, those were just a few of things I started. There was a whole field, and I traced this earliest work, this Lombardi and Raphael, and this paper 67 actually titled Incremental Computation. Okay, and the 68, Michi, I don't know how many people know, this paper is actually called Memo Functions and Machine Learning. It's appeared in Nature, by the way. Okay, so there's so much work, and the one sort of anyway, among these they went just so wide are these things called the transformational programming, which you start with specifications, you do transformations, and you get the programs you want. Okay, and there's just so much. So I only single out one of them, settle. Okay, and you do finite differencing on it. Okay, and settle was created by Jack Schwartz at NYU in the maybe even 60s, but that for sure, for instance, I saw in the 70s. What I want to mention about it was actually Python, okay, is a descendant of settle, just beautiful. All right, so when it comes to me, of course, with all those frameworks, Tim did the same thing. He always looking for the general things. So what I formulated for my thesis proposal is something like this. You're given an F, that's what we've seen from the very beginning, right? A program is an F, but also a plus, talking about input changes. So F takes X and produce some result, and X takes some new things and produce a new input. So once you're given this, what you want to do is compute Fx plus Y. Of course, you can compute from scratch, but you want to use the result of Fx. Okay, so that if Fx plus Y equals some R prime, then apply this F prime. Of course, you take X and Y, but it also takes R as argument. You produce the same result. Okay, and this is the key thing I want to talk about is incrementalization as program transformation. Okay, so the incrementalization takes F and plus give you F prime. All right, and so that's, if you think it's even a prime, indeed it's like derivative. That's why Bob Page called it the finite differencing. Okay, And now you can look at even attribute grammar, those general things are really, and of course I put the ... There's zillions of work on particular incremental algorithms, and those are particular F, right, function, or particular kind of plus, or particular language for writing F and plus. And you want this general thing to apply. Okay. So in fact, the partial evaluation and incremental computation has a really interesting, actually, that's the very first POPL I attended in January 1993. There are 2 tutorials. One is called partial evaluation, the other one called incremental computation. Okay. In fact, that's the first time, as far as I know, POPL ever had anything besides just a list of papers that have tutorials. In fact, they didn't have anything, I believe, until the 20s, except like 2 invited talks later in the 90s. Okay, but the thing I want to emphasize is specialization and incrementalization. Okay, and of course, these things being so powerful, there are math, principles underlying them. The famous Kleinius-SMN theorem and incrementalization. I already mentioned that it's like differentiation, except that this is all in discrete domain versus differentiation is in the continuous domain. And if you look at SMN theorem, the proof is actually not doing anything smart, right? Just, given first M argument, hold it, don't do anything. And if you take the remaining N argument, then apply the whole thing. But the idea, we're so powerful in programming languages and compiler, we can do as much as possible on the first given M argument, and we can do the rest fast. Okay, so here's just a summary, overview of what I think. Partial evaluation is intrinsic in language processing, the very core of computer science. You automate anything, you have a language and being processed. That's the compiler course I consider the single most important course. Generalized partial evaluation is also used in incrementalization. And incrementalization is powerful in general computations and optimizations, like the algorithm course, okay? So partial evaluation, you can think of it, it's like incrementalization applied to a particular class, right? It takes 2 part argument and Y, and you keep one part and get the other part to be completely new. Okay, but the key thing is these things, the idea has been there forever. Even partial evaluation literature I searched before 1990 is like 100, mentions in Google Scholar. A lot of them are not about our partial evaluation and incremental computation, but to do them in a systematic way and automatic way. That's what's unique, right, in language research. Okay, so I just want to this relate all that workshop partial evaluation. I'm just talking about this one slide, right? I call it a meta transformation because it applies to any F, any partition of input, right? X1, X2. So the key idea is, okay, I'm going to try to do as much as possible given the known value of V1 of X1. That's really the key idea, okay? And it's so generalized at any F, any partition, any language to write them. And the general analysis, binding time analysis, if you're powerful, you can self-applicate to the P, apply to P. And this is really has been used in all kinds of applications, right? Later, people research too, dynamic compilation, even new terms invented, right? A lot of talk this morning to runtime code generation, the JIT compilation also, okay? But what I'm going to talk about more is this incrementalization transformation and its power, okay? So we've seen the incrementalization takes the F and plus and give you F prime. And what I did for my thesis is only for recursive functions. Okay, and the transformation I really wanted to mention, this is the style of transformation was really inspired by the transformation for partial evaluation, try to be systematic, trying to be automatic, versus a lot of really powerful transformations in transformational programming. And there it's a semi-automatic or just eureka, pull a rabbit out of your hat. So here the basic idea is you try to compute the fx plus y. Okay, do all kinds of transformation to use the result of fx, that's called R. Okay, so that's what you saw. I formulated this before, but that was straightforward. So the little idea, and turned out that was just problem 1. So that's called exploit the result. So how do you do the transformation? You just do the expansion, right? There are definitions, right? This can be a list adding a new element. And if you ever say take the first element out, right? Y is the new element. So anyway, you separate computation on X from those on Y as much as possible. For those on X, you look, if there are any part is just fx, then you replace that with R. Okay, and more interesting, of course, you don't just explore just the whole X. R can be some data structure, a pair. You can explore parts of it. And also you don't, interesting computation have these conditions. So you can explore under conditions. Under some conditions, it returns this, some condition return that. You explore the conditions. Okay, so that's what all this is about. And what's really interesting is, of course, you think, wow, that was the essence, so you're done, right? But of course, that's actually, if you think about, even though I worked several years on that, it looked too simple. What if FX compute a lot of things and return one tiny thing at the end? No matter how you explore the results, it's not going to be enough, right? You have to explore something in the middle, like Fibonacci. Okay, I compute Fibonacci, right? It's an exponential thing. And then I want to compute the Fib x plus 1. Okay, gee, how do I know which one to use? Of course, that's trivial for Fibonacci, but in general, it's a huge computation. So it's actually a much harder problem. Okay, that's why the memo functions, right? That's the hardest thing was caching. I know caching is going to help, but what to cache? I run out of space, right? So this is the P2. Okay, cache independent result. And so the solution, the general solution, actually, there are two solutions. One's called a cache and prune. One is called a selective caching. Both of them reduce the hard problem to P1, actually. So cache and prune just says, I transform my program to return everything in the result, right? I'm not going to run that. Even I run, it's the same complexity, just huge space potentially, okay? And then with that function return everything, I apply, P1. And then I can decide only for the part I need as the original output, I can delete all the ones I do not need, okay? So you get the right thing to cache, or you can be selective, okay? So so that actually is a huge number more examples you can do, but still not enough, okay? So generally, if you are, in fact, I remember Tim Teitelbaum was telling me, hey, Tom said there were these things he invented that wasn't anywhere there. How can you discover those? Okay, so there are things I do not compute into intermediate result or the result, but I know if I'm expecting a change, it will be helpful. Okay, so here is the idea. I call them discover auxiliary information. Okay, so you take, again, fx plus y, you find all computations on x. Some are the same as fx, some are the same as part of fx. But is there anything left on x that wasn't computed in the fx, but now you need it for x plus y? That's a candidate auxiliary information. So this problem is reduced to P1, just find the remaining ones. And then for those, you cache them, store them, and use them, and reduce P2. Okay. This was actually implemented in the synthesizer generator. Remember, Tim Teitelbaum and Tom Reps, they had this amazing system. It's interactive program environments, actually. So it's not complete automatic. You don't press a button and here's incrementalize the program. But there was a huge advantage. These transformations are very, very non-trivial. If I just give you input and come out output, it's like, how did you come up with this? So the interactiveness really, really helped. Okay, and our later transformations are all automated. Okay. In fact, now it's so automated where I'm trying to add the interactive aspect so you can see it. Okay, so I'll give one small example. This is the famous Fibonacci function that defined to be, right, fib n, there's some base case. The key thing is the fib n minus 1 plus fib n minus 2. So how do you do the incremental version? You apply fib on n plus 1. So I'm giving an f, I give a plus. Suppose the plus I gave is plus 1. Of course, I can just compute the fib n plus 1, but that will be exponential by this function. But you do is you put fib on n plus 1. Okay, you take the definition, you expand it. So you can actually easily see that n minus 1, when n becomes n plus 1, this is just fib n. And this one is just n plus 1 minus 1, so fib n minus 1. So you can already see fib n, you just use the cache result. But fib n minus 1, gosh, it wasn't in the result, but it's in the intermediate result, right? So you cache it. And here is the resulting program, the extended program, okay? So I just return a pair. And the first case, there's no, the corresponding, fib n minus 1, and this one is 0. So I put this in the value, and this is the final result. This is additional value. So now with this, you can see if now I do fib extend n plus 1, and then, so this one becomes fib n. I just use the result, okay? And then this this new one just becomes the result plus PEPM'-1, which is saved in the second components. Okay, so that's, I won't bother writing that down. It's simple. Okay, so but what's really interesting, that's the main point of doing incremental computation, is once you're given Fm plus, like fib, I give you +1, then you can have this incrementalization that's trying to find F prime. How do I use this for optimization? If I give you only F, I didn't give you a plus, I just have a function that's inefficient like Fibonacci or any other famous expensive function, how do you optimize it? Okay, well, you can start at nothing, empty, base case, and iterate at step plus. And you compute each step incrementally using F prime. Oh, I forgot, was F prime there? Okay, so that's the F prime. Okay, each step you do F prime if you're given a plus. But I gave you no plus, how do you find it? For Fibonacci, I said that it's +1 for that example. But why do you do +2? Why do you do -1 or plus k or plus half n, right? How do you decide? Well, that was actually a biggest puzzle for many years. And this is the only part I have only a heuristic. But amazingly, it worked for all examples, including example we had absolutely no clue. And this is it. If I was given the plus, I had to handle it. But now I have a choice to get my own plus. Because my only tool here is incremental, which reuse the result. We all know you minimize change, you can maximize reuse. So then I pick the minimum. Okay, so that's the idea. So for Fibonacci, what you can actually already see in the recursive definition, of course, is always going down, right? Fib_1, Fib_2. So the smaller one going up is +1. Okay. So this is what I call optimization by incrementalization. And in fact, the idea of finding a plus and you keep applying the incremental version is exactly like integration by differentiation. Okay, for those who still remember calculus, I actually didn't realize this myself. I was told this actually by Anil Nirod. So the whole method actually had 3 steps. And actually one of my students, Tom Rothmo, after I had a list of choices, picked the I, even though it looked like the third. So the first step is determine the minimum increment to take repeatedly and iteratively, right? Just keep applying it. And then the second step is the key, it's to incrementalize. Make expensive computation in each iteration incremental, okay, by using and maintain even additional values, okay? And finally, if you have a high-level language, even when this is all finished, you're doing, set computations, adding one element to the set. But how do you represent the set? Okay, so you can design data structures for efficiently storing and access the values needed. Okay, that's the 3 steps. And this is the power. This principle I said so far, it's general. It's not limited to the functions I've seen. Indeed, this applies to any program language. It's just like partial evaluation, okay? Except there's something more powerful in looking at each kind of language abstraction. So when you have just loops and arrays, that's just mimicking what's the well-known machine, right? Closely. When you do incrementalize, these are no extremely high-level abstraction. It's just loops and arrays. Okay, you just apply incrementalize. The loops are already there. You just take whatever expensive in the body, you try to incrementalize. And then it's just a machine on arrays already, right? A consecutive memory, there's nothing to design data structure for. But if you have a sets, that's a high-level data type. So it gives you a data abstraction. You do not have to say it's a list in some order or trees. You can tree just set up pairs, parent and children. So you give arbitrary sets in your data. So you do incrementalize as before, but afterwards you have to say how do you implement these sets as linked list arrays and hash tables. Okay, and the other direction, if you have recursion, okay, and that's a control abstraction, right? Because recursion, that's just a beautiful math. You don't have to say a fixed loop order. So there you have to first decide how to iterate, like Fibonacci, right? You have to decide +1, for example. And then you apply incrementalize. And most functional languages do not do high-level data types and sets, or even they do it so inefficient, people don't use them. So you do have to implement it, just a list, no implement. But what's really powerful when you have a logic rules, okay, and you really need to incrementalize and iterate before and implement after, so you have both data and control abstraction. Okay, and finally, objects. And this doesn't add any of those abstractions, just module abstraction. You have to do incrementalize across components. And this iterate and incrementalize is exactly integration by differentiation. I mentioned that Anil Nirod first told me this when I did my thesis proposal. I didn't even have integration or iteration part. I just did incrementalization. And he said, you're doing integration by differentiation. It took me 3 years to understand what he's saying. And among all these different abstractions, I mentioned we did recursion. A lot of people did recursion too. But Bob Page and at NYU and Jack Schwartz had sets. Okay, so of course, all of us afterwards, we did loops. It's just trivial. But and then of course, when I came to Stony Brook, they have the world's best experts in especially fish implementation, by the way. So I did it for rules. But turned out actually, I really among all my students, Tom Rothmel stood out. He was the one actually did more systematically for sets and objects. Okay, because even though Bob Page had sets, he has a built-in set of rules. Okay, you manually write the rules, you apply automatically, but what's the general principle? How do you generate the rules? Or I don't even need the rules at all. Okay, so that's what we have. I won't go through detail, but the point was we apply this to all these examples. And the point is a powerful method is for each of these I talk about, we end up with new or input algorithms or better complexities than before. Okay, and then some of them with even new languages and new specifications, better specifications. Okay, so next thing is, how do I do, once you have this thing on loops and sets, recursion and rules and objects, and obvious the next thing is, well, these objects can be concurrent and distributed. And for rules, of course, I started with simple data log rules, and you can do many, many rules, but that looks so hard. I've been trying for 20 years since I came to Stony Brook. Rules look simple, but it's hard. So I will quickly give you 2 examples, and we'll do the last 2. Okay, so I said even for the, let's go back, even for the simplest example, we find new things. So recursion to iteration, I want to use the smallest example, factorial. So what new can you find about factorial? That's what I was surprised too. Everything was surprised. So, right, this is your definition of factorial. 0 is 1, else n times factorial n-1. And this is a recursion. That's actually the most used example in textbooks for program language teaching intro to programming and recursion and stacks, saying this has recursion takes not only linear number multiplications but linear space, which it shouldn't happen. So you can make an iterative version, and for a lot of programming people like write functional programming, you just make a separate argument r, additional argument r, that was accumulating the result. Okay, so you come in here, you say, okay, I just put r as an actual argument, and every time I get and come down, I say comma, n times r, just keep accumulating until n equals 0, I return r. Okay, that's the most famous tail recursion code. So I'm going to show you that. It's on the right here. Okay, you can return r, otherwise I just do this. And I like to write iterative version just because, for us, we say, what's the plus, what's iterative? But anyway, the corresponding iterative version look like this, right? You start with 1, and then you do the multiplication, do the minus, and this is equals 0 returns r, not equals 0, otherwise return r. Although this one actually is not a complete program. To be complete, you need to add saying, call with r equals 1. Okay, so what's interesting about this? Well, I tell you, our incrementalization doesn't derive the program on the left or on the right. Okay, we are not that smart to say just one variable and now multiply n and keep going down, return result. We do the most dumb thing, which is incremental, right? You computed the PEPM'-1, I multiply n on top of it. So I need an actual argument that says, okay, this is n, I need an actual argument that start with 0 and keep going up and do multiplication. Okay, so what's happening? I get a program slightly more complex than this with one actual argument. But what you cannot believe is this program, when I was assistant professor in Indiana University, they have the best scheme compiler. You put in this program, okay, it's slower than the original program. And because you're doing multiplication, this is multiplying smaller number first, this is multiplying bigger number first. You need associativity to change the order. We derive this one, which has n1 start with 0 and keep going up until n. Okay, that's just dumb incremental computation. And this one is the fastest and need no special associativity. Okay, and I was going around asking people, nobody knew this until I think Torben Morgensen, when I was at DIHO actually, Neil Jones invited me to come and give talk, and he was so far the only one to say, yes, that's why mathematicians actually study special algorithms to compute factorial, because the most efficient algorithm wasn't to compute multiply smaller numbers either, because factorial is a big number, you multiply smaller numbers, right? It's getting smaller. After you multiply to a certain point, it's getting expensive. Okay, so I'll give you one more example about the rules. Okay, these are really about the sets and relations. Okay, you're given a set of edges with just a set of pairs, and you want to compute the transitive closure, right? That's a very famous thing. Imagine a graph, and if you try to write this in your C code or any other language, just think how to represent the data, how to do the loops, and if you take algorithm courses called the depth first search or the breadth first search or adjacency list or transitive matrix, but using data log, you just write these two rules. If I edge from U to V, there's path from U to V. There's edge from U to V, there's path from use W to V, then there's path. That's it. Okay, but the point is these are sets or relations. It's the same thing. Okay, you give us a bunch of set edge sets or relation, you want to compute the path. Okay, and to apply a method, iterate. Remember, iterate means minimize. So every time I'm going to infer one more, pairs. How do I do? Consider one fact at a time. That's the minimum change, one at a time. And incrementalizes all these sets. You want to compute the sets efficiently. That's the key. And there is called indexing. Okay, and then the data structures generate linked lists and arrays automatically, of course. And the key thing about this is because it's so high level, okay, even than just set language or recursion, of course, is even lower level, you can actually stare at the rules and know the precise complexity. Okay, so the cost model is number of times the rule fires, because the data structure we generate guarantee every time you add a fact, it takes worst case constant time. Okay, and the space for storing the set. So even if you do not know the method, you can actually know the complexity. It's just number of combinations the rule was fired. So the first rule fired only number of edge times, right? Each one you add a path. The second one, how many possible combinations? There are two ways to count. In fact, that's the optimal, right? Because you have to consider all combinations. If you enumerate all the edges and W is fixed, that means for each W, you have to look at how many V. Okay, that's called the, passed out the two second argument given the first argument. Or you enumerate all possible paths and you say, given the second argument, how many the first argument. And both are upper bound. And the complexity we actually run is the minimum. Okay, it can be even smaller than this, right? Because both are upper bounds. And for space, the method that says you have to look backwards. So there's the inverse. Oh, I forgot to say, edge is edge, and paths given, this is the number of vertices in the worst case, and the path, of course, is output, and edge, this is the integrate. So the complexity is actually time or edge times vertex. If you take algorithm textbook, they tell the complexity is like n square, but this is a lot more efficient, right? Most real world application isn't isn't dense. So this is like n square. And then if you actually know the output, which you have to for any computation, in fact, if you change this order, it becomes out degree. In all computer programs, out degree is constant, or depending on how you model it, of course, then the whole program is linear instead of cubic, you think. Oopsie, I didn't, oh yeah, okay, I'm for space. I said this storing the inverse map takes this, okay. So the last part is about the distributed computing. So I said we have objects, you think object can be concurrent and distributed. So very first thing, you have to study these algorithms. I have to say, even the simplest distributed algorithm is just infinitely more interesting than centralized sequential algorithms, because these messages can be arbitrarily delayed. Okay, it just unbounded behavior, just exciting. But how do you study? Okay, in terms of language perspective, of course, you write pseudocode. And there you have a high-level idea, but it's imprecise. Of course, there's so much actually, especially a formal method, people study concurrent and distributed system in specification language. There they get precise semantics, but often, or it's not high level enough and just hard to understand, right? And then, of course, we build real systems. People, most people do not study formal specification. They write programs. That's what your system running, all including this, right? And those are executable. They have to run. So we want to study this systematically. The very first thing, we need a language, because when I was teaching this, right, in Python, I've been using for years, just make sure to put the colon indentation, your pseudocode runs. But for distributed computing, it's a totally different story. It's a huge literature, all different languages. So I wanted to combine the best of all of them. Okay, so we have a language called the DistAlgo that does combine all three. Okay. So of course, our research apply everything we have studied, the compilers, optimizations, but also these particular examples. Again, for each one, we want to find improved algorithms or better specification, more correct specifications. Okay, we also study checkings and so on. Okay, these are separate references, but I'm just going to give you one example to show you the key ideas. Okay. Just one, right. The one slide is about this language. It's extension to all languages, just like objects now distributed. Okay, and so the language allow you to say these process is a distributed objects, right? You can send messages, just like create a process, create the object and send message. And you have control flow to say what you do when you receive the messages. And the key interesting things is this: you can do queries, high-level queries on message histories, all the message you ever sent and received. The queries can return sets, sequence, can return aggregation, count, max, and quantification for all exists. And finally, you can configure the system, right? Just imagine setting up all the system in a distributed way and run. Okay. The key thing I mentioned is these called the history variables, which were already in the study of distributed systems forever. Okay, but nobody dared to think about putting a programming language because these are histories, right? If you run it, it's unbounded. It's be there forever. It's the biggest memory leak. Okay, and in distributed system, it's a full lots of quantification, right? Is there some process did something? All students, right? All process have replied something, some on each. That's for all one exist. Like okay, and we now have to do those incrementalization systematically. Okay, I said we did the sets, but we didn't do quantification before. So I gave you a simple example. Would these algorithm description look like this? And this is one of the best one because Lamport, right, is very famous for developing pixels. And there's a long story how long that take to publish, but then he later wrote this one called The Pixels Made Simple. And this is the best description. You can just read a couple lines to get an idea, right? A proposer select a proposal number and send a prepare request with this number to majority. And if acceptor receives a prepare request with number of n greater than that of any prepare request which it has already responded, then it does this. Right? So there are a lot of things you feel like select a proposal number, but what number? Okay, and if right, there's a lot of those things. Turn out that these people are so expert that when they don't say something, that means it can be anything. You can select any number. Okay, so how do you turn it into code and make it run? Okay, and this the part I read was the simpler part. The two middle part of these is the most complex one. Okay, so once you already have high-level sets and high-level quantifications, and this is it in this algo on the left. Okay, this is everything on the previous slides, and on the right were the comments. So you can see there are proposers, acceptors, and learners. That's a bit, I didn't read it. And then you can set up, majorities. And then let's say select n, it didn't say anything. The most common thing to do with system when you have nothing, take myself, okay, and send prepare n to the majority. So this is the send, and you have this receive, right? You receive this message, do something, and also await, this is a synchronous receive. Let's see. But anyway, so that's the whole point of you can write precisely as a high-level language. But what I want to show you is it's not this detail. As I put the next slide, is just like this, except I put old is exactly this one. You can see I just increase the space a little bit. I put all the queries in red. Now you can see every non-red part was totally trivial. Do assignments, send, right? Wait false means just keep waiting, handling message, send, right? Just pass to nothing. And the only thing interesting are these queries, okay? And these are count, right? That's like the aggregation, and this is aggregation, select any one of the set, and this return a whole set, and the each and the sum, that's the quantifications. Okay, so those are all over sets. So here the received, okay, that's a history variable. Receive a tuple is the same as tuple in the received sequence. That's like logic program, right? Edge AB means the pair AB in the edge set. So you just write this, and the point was you write the hello specifications, and these queries are extremely expensive, but they are all about the sent and received in distributed systems. So you can incrementalize these queries with respect to change, which is your add or delete. Well, actually, don't even delete. The history, your new message you sent, new message received, that's the delta. That's the plus operation. Okay. And so actually, to make sure that this is complete program without 31 lines, plus these lines for creating processes and set them up and start. I use the ideal syntax in the slides, but our implementation was in Python. We have a version, of course, with this ideal syntax, but this version, you don't have to do anything to Python. So you don't say process P, you say class P, extend process. You don't say send to P, you have to put a parenthesis and equal. Okay, so that's this complete language. And that particular thing, you probably guessed the idea. I give some example here, like some element in S has this property. In fact, in distributed system, and the algorithms that's full of these conditions. And that actually really, really helped us study of logics, because that's what I'm trying to study since I came to Stony Brook. Those are, or you in your probably your first discrete math course, right? But they're hard to understand. And the rules I show for transitive closure is very simple and clear. But if you have a negation in it, and turn out the semantics is totally difficult. So here is one of the most famous example, Russell's paradox. A barber shaves those who do not shave themselves. That sounds perfectly fine, right? Now the question is, does the barber shave himself? If he shaves himself, right? Barber only shave those who do not shave themselves, then he shouldn't shave. But if he doesn't shave himself, then he should shave. Gee, that's the most famous paradox. Okay, what's the meaning of the sentence, and what's the answer to that query? Okay, so the key difficulty, not a particular paradox, is there's recursion. I'm defining shave using shave and with a negation. Okay, turn out there are many, many semantics and all very solidly defined, but they're, subtle, right? These sentences are subtle and could be tricky. Try a little variation, is a whole different thing. And also brittle. Something feels like it should continue, but then everything changed, or restricted. I cannot allow you to say this. And so all these, they do not disagree with the meaning. So how do you communicate if people say the sentence and have different meanings? Okay, so our work is what we call founded semantics and constrained semantics. We say it's simple and it's unified. Okay, this is some references. So the key inside is different disagreeing semantics. This is not like denotational semantics or axiomatic semantics. They're different, but they agree. These are disagreeing semantics. It's because they have different underlying assumptions. The things you have to capture the assumption. But what are the assumptions? Some of you have heard open word assumption, closed word assumption. That's only two names ever. Nobody defined them precisely. In fact, there's so many more semantics all under closed word assumption, or right? So which one? Or open word assumption? So here's our solution. You capture these all assumptions by simple binary declarations. And the semantics is simple. It's just a least fixed point, just like for transitive closure, or constraints. Think about logical rules that are logical constraints. If this is true, that is true, then that's a constraint. So it's completely declarative, not like some of these are very complex semantics. Okay, so the binary declarations are just these. For each predicate, you can say whether you're certain or not. If you have only positive dependencies, of course it's certain. Otherwise, you cannot be certain, it's uncertain. And for those uncertain, you have to say for that predicate, it's complete or not. Means everything defining that predicate is given or not. And there's one last choice, actually. Anyway, it's actually can go back to certain. So for Barber's paradox, you can think about that. You can write this rule. Barber shaves X if X does not shave X. So if you put a Barber in here, of course, Barber shaves Barber if Barber doesn't shave Barber. So they're based on constraint semantics. It can be at least fixed point. In fact, you can ask, does Barber shave Tom? There's nothing says Tom shaves himself, so Barbara shaves Tom. Okay. By the way, if Tom does shave himself, then Barbara doesn't shave him. It's actually right. It's only for Barbara that wasn't clear. So depending on if you choose font-based semantics, that just every sentence doesn't have to define everything. So for this particular one, it wasn't defined. If you assume it's complete, by the way. If you didn't say this rule is complete, well, there can be other shave facts. If you put in, you can doing the same inference. Okay, but if you do require everybody has a unique one, then indeed this has called a no model, no solution. Okay, but the point is you make the assumptions clear. Okay, which one of this and which of the choice you're taking. And just binary, there's not like complicated alternating fixed points, read out, all that stuff. Okay, so since you did that, you can see one of the most actually the most famous complex example. Essentially, almost all games has this interesting aspect. It can be described as one rule. A game, you're given a bunch of moves, right, from some position to some other position. And there's one rule to decide what are the winning positions. So X is the winning position if you can move from X to Y, and Y is not the winning position. You think about it, it's like even your chess, right? You can go somewhere, that guy cannot move anymore. But what's the meaning, right? What's the exact semantics? So I give you a bunch of moves. Can you decide what are the winning, losing position? Maybe some remaining one that's draw positions. How do you decide that? You can actually do this yourself. So very first thing is quantification. In all data rules, except it has negation, but it's the same thing. You write down exactly what it means, right? It means exist Y, you can move to, and that's not the winning. And since I said make the assumptions explicit, by the way, this is also the default is complete. There's no other rules define this. So which means if this condition isn't satisfied, then this is false. So you add a completion rule. Not if I just reverse the whole thing, right? For all become, some become for all and become more, not, right? Just exactly add the completion rule. That's the inverse rule. Now you actually can understand these are can be made monotonic, right? The part thing of Russell's paradox is not monotonic. So you name negation for not something, you add n dot something to make it like a predicate. Okay, so n dot something, n dot something. So in these two, that's what exactly these two rules mean. But there's no negation anymore. If you look at the definition, it's actually monotonic. Okay, because you're given moves, all the rest possible places, that's just n dot move. That's a positive. All these are positive. You just infer more. So you do least fixed point, you keep inferring. So for this particular rule, actually this second rule is the base case, right? For all Y, either you have no move to or that place is win. So if you have no place to move to at all, you satisfy this. That's a losing position. That's a n dot win position. Once you have that, you can infer more win. And you just keep, when you have more win, you can come here and infer more of this, and you're just doing the same loop as before. Okay, so that's the least fixed point. Okay, infer n dot win when X has no moves, and infer Y, and just repeat, just like least fixed point. And when you're all finished, okay, name it back. N dot win, that's the losing position. So you have win being true, win being false, and the remaining ones are the draw positions. And by the way, this is linear time. Okay, so, all right. And the last example, this is probably just as famous example as the other one. But this is much harder because it needs aggregation. Okay, so C is a company, and company C1 owns P% shares of stock of company C2. You're given these two. And now this is one to compute. This company C1 controls company C2. That's the case if the sum of percentage of shares of C2 owned either directly by C1 or by companies controlled by C1 is more than 50%. I remember reading this for 20 years. I do not understand. I can't think. And there are many more semantics proposed. In fact, this is recursion with aggregation because I have a count in the recursion. Okay, and this is actually even much harder than negation because negation just essentially equals count equals 0. Now there's counts being different. Somebody can be true and false, and happen to add up to be that number. Okay, but when this is written down exactly like rules, in fact, this is copied from one of the papers. And if you just use the simple thing we have, you look at the rules. Okay, this positive thing infers that, the positive things infers that, and the sum greater than 50. These are percentages or positive. Some, if you add more, the sum will be more true. So this is completely positive. There's not even negation of any sort. So for this most famous example, okay, it's just, you just start from base case, what's true at the result, what's true at the result, at least fixed point, you get the answer. Okay, that's it, as simple as that. Okay. By I said by default that they are all certain, there's nothing negative, and just a fixed point. In fact, there's so many papers on recursion with negation as before, but there's even more on recursion with aggregation, and give different meanings, or say that you cannot write this program and write differently, or just say I cannot compute this meaning. Okay, so just in the spirit of being programming language, we have this semantics, and we want to be sure we compute it correctly, right? So these are all most famous systems except DA, DistAlgo, and DistAlgo with incrementalization. But this DLV, XSB, Klingo, those, you can see the performance. The DLV, by the way, DLV new version doesn't handle aggregation. This is an old version. And DA, of course, without optimization with expensive quantifications. And then this was, what is this one? Blue is XSB, and the Klingo. And this is actually incrementalization, apply the systematic incrementalization to this program. Okay, this particular one actually wasn't done automatically, but it's just turning the crank. Unfortunately, we had all those implementations, as you know, right? Python, we had the Python 2, Python 3, and even now Python keep upgrading their compiler. We have to keep upgrading. But we actually found, we didn't find that XSB expert found, hey, why XSB is so slow? Turned out you can delete the company facts in the rule hypothesis, and XSB improved asymptotically. But this had to be found by experiments running on data, bigger data, to find what happened. And still, that now it's fast. XSB is faster, but still twice as slow as the Python, right? This is really Python implementalized. But what's interesting was, because you have quantifications, aggregations, okay? So remember the win example? I made up this double win example because I said that the most famous example of company control, it turned out to be trivial. So I took the win example to say, well, if the number place you can move to that's not winning is at least 2, right? Remember the win example, just there's one place you move to that's a winning. So let's do a count. Then that's the reason actually we want to know what other systems produce, right? The company control was just, our interest wasn't to compute efficiency, then just have to run it. I happened to notice that. Turned out, of course, Klingo and DLV, these compute unsuccessful semantics, they couldn't compute when rule draw. And if you have a odd cycle, there's like no model. Or if you have an even cycles, like exponential number of cycles, incremental number of models. Okay, so, and XSB, and actually for some of our examples, produce incorrect result. Okay, but logic rule engine has the magic. You can query each individual one, not compute all of them. If you query each individual one, they actually produce the same as our result. And we also recently learned, actually, SWI prolog are extended to compute the semantics SSB, except for a smallest input, give incorrect result. But they both recently, that they found and fixed bugs that cause these incorrect result. Just to finish, in fact, look at these two. Here's one we didn't put in the papers yet, right? If I have a language that allows condition, allows count, I should be right this one, right? It looks the same, just with a small change. And these two are both, and of course, Klingo and DLV cannot compute it, but XSB as a product, they don't get correct answer. In fact, both David Warren and Jan Vellinger said, gee, I do not see our semantics or whatever the current algorithm can never give the correct answer. But I know XSB at least has been actively working on it, try to compute the correct answer. Okay, so to conclude, I just give a quick overview of the frameworks of partial evaluation and increment computation, and emphasizing the power of doing these transformations systematically. And the power first lead you to have really better understanding of what's underlying optimization, okay? And so you can get improved or new algorithms, right? Not just derive what's there. Or we do that too, of course, all of them, but just the interesting ones. And with precise complexity guarantees, okay? And then even more was once you have those implementation method, you understand, oh, I can actually write something simple and more straightforward. So we have higher and higher level language to allow you to program and creating new programs easily and give simple semantics for understanding. Okay, so there's a lot of ongoing work, and I didn't expect, I don't know if Fritz is here, I actually had a reference to him. Of course, we are studying, that's our key, efficient implementations, complexity guarantees, and more powerful language for rules and constraints. Okay, including, now I said I want interactive even graphics. And of course, all those examples you've seen, those are applications. But one particular one we would like to is for teaching and learning. I made this general, is really, it should be both human learning and machine learning. Indeed, I mentioned automatic differentiation as you use all these neural networks. And to do that efficiently, you're actually doing, partial evaluation and incrementalization. And Fritz Henlein has been doing some amazing work on that. Okay, that's all.
All right, let's thank our speaker. Are there any questions? So I don't see any questions in the Q&A tab. I see one question in the chat. This is from Cody, who asks, I think this was around slide 15 when you were introducing optimization by incrementalization. Cody asks, is this integration by parts?
Not right. You understand integration by parts is not the same as integration by differentiation. But integration by part has something interesting. I have to tell you one thing interesting. Of course, I learned more math than computer science, even though I was a CS major, because we didn't have computer when I was at Peking University. We have very few. But I forgot all of that, right? Which was a neural that was telling me you're doing integration by differentiation. So I end up having this opposite order every time I have some new thing. I talk to neural, then neural saying, you're doing this. And then he would say, you will be doing that. So that's what I've been trying to see him every year and to find out what I will be doing 3 years later. Great question. There will be, for those new kids studying calculus, or even you remember well, you should be thinking all the optimizations are really differentiation. It's just you write manually, right? You have to do every step, updating the states efficiently. Okay. Yeah, this seems like that's the only way to go back to my slides is to click on this this little arrow in here, and it's so slow.
All right, thank you. Are there other questions? Is there anyone, Paulette? Okay, so there are no hands up. So I had one question. So you gave a very motivating talk with lots of great examples about the systematic approach to incrementalization, and even gave us a recipe for it. But I was wondering, how much of this do you think is automatable? A lot of your examples seem to require a bunch of human insight, but you also mentioned that there was some automated transformation.
Yeah, that's absolutely critical. In fact, the factorial example, that's what I did for my thesis, and Fibonacci, those recursive functions, those are semi-automatic implementation. We did have an automated implementation, but it was since the generator stopped working. But everything else we did, okay, everything else we did was fully automatic. Okay, in fact, by the way, this is my book in Compilation Press. There are hundreds of references, including, of course, our work, but built on all previous work. And in particular, right, for data log rules, of course, you generate the sort of optimal, in the sense I described, implementation from just those rules, and for sets and objects too. Okay, so we actually had all these implementations. Those were before people are used to getting everything on GitHub. But we do, DistAlgo, of course, is on GitHub, and we use for hundreds of projects for distributed system courses. But for the other ones, right, I said most of them are implemented in Python 2 and so on. We didn't upgrade them. We're still figuring out the semantics of logic languages. But I think we will be going back to upgrade those and hopefully put all together. That's an excellent question. Indeed, recursion is relatively lower level in terms of data. You see, right? It's just control abstraction. People just write a list in order. Okay, so to automate those, it's hard. I struggled hard for my thesis. You add a new element, you better at the beginning of the list. If you somewhere in the list, you're totally blown up with a linear factor. But when you have sets, the order doesn't matter. In fact, almost all time, in fact, database, right? The state sets is really database programming. This order doesn't matter. And when whatever order matters, you do a sort. Okay, and that's really how all the power comes in. In fact, I mentioned this thanks to the giants. Nero told me this. In fact, Nero has related this to for 20 years before. He was telling me you were doing math, and then some more recent year, he telling me you're doing physics. And turned out there's this thing in physics, actually, Noether's theorem. That's saying, for those who know a little bit more, was right. Every differentiable symmetric function has a law of conservation. And of course, the differentiable understood that's this, but the symmetric, okay, you understand with sets, I gave you the symmetry, and with the list, you're stuck. So yeah, it's hard to automate the arbitrary recursion on lower level lists. But when we have rules, right, those rules you see the example, those are recursion over sets, and it's just at least fixed point. So that's the most power, which is the sets, which is why database is a whole separate industry.
Okay, thank you very much. So I think we have time for one more question, and we have a question in the chat. Is it displaying?
Oh, can you,
okay.
Tom Reps, can you do aggregation problem with the discounted costs? I don't know what the discounted cost means. Can they speak? Or I found it's really slow to type.
Yeah, that's okay. Can we add Thomas to the stage? Okay. All right, we're trying to add Thomas to the stage if they can join, if their microphone will work.
Yeah, can I be heard? Hi, Annie.
Yeah, hi, Tom.
So with discounted cost is something where with every extra step of a longer path, the reward goes down by a factor of gamma for some gamma between 0 and 1.
So what was your question again? Let me check.
I guess what I'm thinking about is a lot of your. I mean, I've worked a lot on problems expressed as semi-ring problems. So there you have, I mean, your aggregates. I won't use plus because you use plus for something else. But the aggregate operation is like the semi-ring combine operation. And then one of the things that you can use in the semi-ring extend operation is a discounting factor. So your problems seem to have a semi-ring combine, and I was just wondering whether you can also handle what in semi-rings, what would be the semi-ring extend?
Well, actually, I still didn't understand this discount thing, because right, for our optimization to work, right, you have a precise language, you have a precise meaning, and all you do is follow that meaning.
Suppose you want this. So suppose you want you can define a variation of the shortest distance problem, where every edge has a length, but the length is discounted if you have to use it case steps from the beginning of your path. It counts only length times gamma to the k, and so you're not just summing the edges as you go along the path, you're discounting as you go along.
Oh, that's what you meant, the discount. I see. That's a sort of implementation perspective.
It's exactly this. It's exactly the same thing as that you have in the financial industry. If you have an amount of money now versus having an amount of money in the future. When a lottery is paid off, they don't give you $1 million. They give you $600,000 because over the next, in 20 years, it will have given interest. So like present value in financial calculations.
Okay, so well, first of all, the more direct answer to the shortest path question, of course, you can just write that's what actually I did, even just a little extension to my thesis for all the several famous shortest path algorithms. You can just write the recursive functions, and you apply incrementalization, and you derive the famous whatever the textbook algorithm in dynamic programming to achieve those. And then, of course, we haven't done anything using recursive function for some time. So, of course, logic program people, you write the rules for those. And then you say, what's the most efficient way to compute it? So, indeed, for our most recent semantics we have, for rules with aggregation, we can do the shortest path example to give you the whatever the optimal path you want. Okay. The point was you're saying, okay, as you go along paths, you don't add it, sure, but because you do not just go along one path, right? You're considering all paths and what's the minimum among all of them. But that's just comes from natural as a part of the exploring the next pair in the edge you add. But that's an interesting name. I didn't know.
All right, I don't want to eat into the break too much, so I want to thank our speaker again, and I'll let you continue this conversation offline if there are more questions. So let's thank our speaker one more time.
Thank you.